Hi, I am Alexa Thomas. Um, and today I am going to be discussing my week 6 case connections. Um, Unfortunately, Zoom isn't loading my slides, so I'm just gonna kind of forego those and walk through my cases verbally. Um, okay, so yeah, the first case that I looked at was case 1. And our first goal was to discuss the normal mechanisms of ammonia transfer in the body that should be occurring, including glutamate dehydrogenase, glutaminase, and glutamine synthesis, synthet synthetase, synthase. Sorry. Um, and then I'm going to discuss the role of transanimation. So, a waste product that comes as a result of degradation of proteins and amino acids in the body is ammonia. And the body has mechanisms that prevent toxicity by ensuring ammonia passes through them for proper disposal. The body's excess ammonia needs to be removed, and glutamate dehydrogenase is one of the enzymes involved. So, glutamate is transformed into alpha ketoglutarate, which releases ammonia. This is a reversible reaction, which results in glutamate and ammonia being produced within the body. It also detoxifies glutamate for ammonia. An enzyme called glutaminase enables ammonia to join with glutamine, forming glutamate. Glutamine is highly important during this process because it helps in transportation of ammonia to the kidney for safe waste disposal, particularly particularly in that kidney area. Um, Glutamine results after combining glutamate with ammonia in a reaction of glutaminase. Glutamine carries ammonia in a less toxic form through the blood circulation until it gets to the necessary tissue to convert it back into glutamate. In terms of transanimation, transanimation is responsible for the conversion of an amino group from an amino acid to a keto acid. And this leads to the creation of different amino acids and keto acids. This process transforms excess amount of ammonia into less toxic compounds, which are in turn useful for elimination and metabolism. Which is in turn useful for either elimination or the metabolism process. And kind of overall, these mechanisms cooperate in balancing the body's ammonia. So this ensures that it is disposed of appropriately, preventing toxic accumulation. High ammonia levels may result in defects of or result from defects in any of those three mentioned systems, leading to neurological dysfunction as well as other very serious medical complications. This is why all of them working together is extremely important for the body to remain healthy. The next question is, how is nitrogen transport connected to glucogenesis in the fasted state? So when fasting, amino acids support glycogenesis. When amino acids break down, nitrogen goes into the liver through transporters like glutamine and alanine. Ammonia is detoxified by this process known as the urea cycle, while carbon compounds for controlling blood sugar levels are produced through glucogenesis. In this particular individual in the case, where uric acid levels are elevated, the urea cycle enzyme, or what urea cycle enzyme is most likely deficient, and what urea cycle enzyme will least likely be impaired. Elevations of uric in patients with deficits in the urea cycle are typical for pathological disease uptake in OTC. The lack of OTC blocks the conversion of ornithine and carbamoyl phosphate to citrulline. It increases uric acid by building carbamoyl phosphate that is directed at the synthesis of the pyrimidines. Citrulline levels here are normal. So things like ASS or ASL would probably be least likely to be affected. And these are the additional enzymes involved lower down in the urea pathway beyond ornithine transcarbamylase. So these enzymes are involved a lot farther downstream in the urea cycle. The last question for case 1 is, which amino acid, if any, becomes essential as a result of this deficiency? And an OTC deficiency prevents ammonia from entering the urea cycle for effective disposal, resulting in its buildup. Hence, other mechanisms are used for the body as substitutes for the main process. These include additional production of glutamine using some more ammonia. This increased requirement of nitrogen for incorporation makes arginine as a precursor of ornithine, which is an intermediate in the urea cycle. Because arginine plays a major role in producing ornithine, lack of OTC supply may lead to insufficient amounts of ornithine and consequently lead to arginine as a conditional essential amino acid. And 1 second. Okay. And the second case that I looked at was case 2. First, under normal conditions, describe the metabolism and maturation of VLDL particles. So the liver produces triglycerides, or also known as TGs, from fatty acids. The TGs, cholesterol, and other specific proteins, such as in apolipoprotein B100, combine to form VLDL particles. TGs, cholesterol, and these other specific proteins are packaged together inside the hepatocyte's endoplasmic reticulum as mature VLDL particles. These, kind of referred to as nursery VLDL particles, are further processed. This is a process where more lipid components are added to the particles. Finally, mature VLDL particles move from the liver into the bloodstream. In the case of mature plasmolipoproteins, lipoprotein lipase, or LPL, degradation occurs at local tissues. And as a result of hydrolysis of triglycerides, VLDL changes into IDL and then finally into LDL. And cholesterol is then transported by the LDL. And the last part of case 2 was to describe how NAFLD could manifest and what potential processes could be impaired in order for this. So NALFD leads to accumulation of fat in the liver, and typically this is linked to excessive weight gain and insulin resistance. A variety of processes can be affected during NAFLD. Fatty acid overflow results from insulin resistance that increases fat entry into the liver in non-alcoholic fatty liver disease. This can come from both your diet or adipose tissues. It stimulates hepatocytes' production of more triglycerides that add onto fat's accumulation. Therefore, NAFLD could also have an influence on VLDL, particle assembly, and secretion. Hepatic fat excess may affect VLDL formation and secretion. This leads to a reduction in the total amount of VLDL that the liver releases into circulation. NAFLD also has the same issues in relation to reduced sensitivity of insulin that cause more problems, which could interfere with the liver function by causing abnormal lipid metabolism. This dysregulation could lead to triglyceride accumulation and an excess of VLDL particles in hepatocytes. These kinds of changes may relate to modification in the manufacturing, storing, and even the export of proteins, of lipids. Finally, non-alcoholic steatohepatitis, sorry, that's a hard word, also known as NASH, may develop due to prolonged deposition of fat in the liver, as well as oxidative stress and inflammation. And this inflammatory response may at times become more severe, resulting in impairment of liver function and promotion of fibrosis. However, it may lead to cirrhosis at the end of the day. So it can definitely lead to more intense diseases. Many sophisticated pathogenesis components like elevated hepatic fat storage, modified VLDL turnover, insulin resistance, inflammation, and oxidation stress are involved in NAFLD. And these processes may become irregular, thus triggering fatty liver disease, which may progress into even worse conditions like cirrhosis, and other advanced liver cases. So could definitely progress and become worse. Anyway, those are my week 6 case connections. And yeah, thank you for listening.